Dick Cantrell stood in the Lockheed Skunk Works library in 1975, holding a translation that would change air warfare forever. The document, an obscure Soviet physics paper from 1962, had been gathering dust in a CIA archive until someone thought to send it to California. Cantrell, a radar specialist who'd spent 15 years making aircraft harder to detect, read the title twice. Method of Edge Waves in the Physical Theory of Diffraction by Pyotr Ufimtsev. The math inside looked dense, almost impenetrable, but Cantrell understood what it meant. Every aircraft flying in 1975, the F-117s, the B-52s, the SR-71s, could be seen by radar because they reflected electromagnetic waves back to their source. Fighter jets showed up on enemy screens like lighthouses in fog. Ufimtsev's equations described exactly how those reflections worked, breaking down the behavior of radar waves when they struck different shapes and surfaces. The Soviet physicist had essentially written an instruction manual for predicting radar visibility. Cantrell brought the paper to Ben Rich, who ran the Skunk Works after Kelly Johnson. Rich had built his career on speed. The SR-71 Blackbird could outrun missiles at Mach 3.2, but speed had limits. Soviet surface-to-air missiles were getting faster, their radar more sensitive. An SA-6 had shot down an Israeli F-4 Phantom over the Golan Heights in 1973, proving that even America's best fighters could die in modern air defense networks. The Air Force needed something beyond speed. They needed invisibility. Rich handed the Ufimtsev paper to Denys Overholser, a 34-year-old radar engineer with a mathematics degree from UCLA. Overholser had joined Lockheed in 1970 specifically to work on radar cross-section reduction, the science of making aircraft smaller on enemy screens. He'd been experimenting with radar-absorbent paint and curved surfaces, trying to shave a few decibels off an aircraft's signature. The Ufimtsev equations suggested something far more radical. Shapes that wouldn't just reduce reflections, but eliminate them almost entirely. The key insight buried in those Soviet formulas was this: radar waves bouncing off an aircraft's surface behaved predictably based on the surface's geometry. Smooth curves scattered waves in multiple directions, but flat panels arranged at precise angles could deflect radar energy away from its source, like mirrors reflecting light anywhere except back at the observer. Ufimtsev had calculated the exact mathematical relationships governing these reflections for edges, corners, and flat surfaces. Overholser spent 3 weeks working through the equations at his Burbank desk, filling notebooks with calculations. The Soviet physicist had focused on theoretical scenarios, simple shapes, ideal conditions. Overholser needed to apply those theories to something that could actually fly. He started sketching aircraft designs composed entirely of flat panels meeting at sharp angles. The shapes looked bizarre. Nothing like conventional jets with their rounded fuselages and swept wings. They looked like folded paper, like geometry lessons, like nothing that could possibly stay airborne. But the radar cross-section numbers Overholser calculated were astonishing. A conventional fighter jet, an F-15 Eagle, had a radar signature of roughly 25 square meters, meaning it reflected radar waves as if it were a flat plate 25 square meters in size. Overholser's faceted design, according to Ufimtsev's math, could theoretically achieve a radar cross-section of 0.01 square meters. That wasn't reduction. That was erasure. On a Soviet radar screen, his aircraft would appear smaller than a sparrow. Rich looked at Overholser's angular sketches and saw either genius or madness. The Air Force was about to find out which. Pyotr Ufimtsev never intended to help America build invisible aircraft. The 40-year-old Soviet physicist had published his equations in 1962 as pure academic research, solving theoretical problems about how electromagnetic waves diffract around objects. He worked at the Moscow Institute of Radio Engineering, calculating wave behaviors that interested maybe 24 specialists worldwide. The Soviet military reviewed his paper, stamped it unclassified, and filed it away as irrelevant to practical defense applications. That decision would haunt Soviet air defense for the next 30 years. The equations Ufimtsev derived, known as the physical theory of diffraction, provided exact mathematical descriptions of how radar energy scattered off edges, corners, and flat surfaces. Previous radar calculations relied on approximations that worked for smooth, curved shapes, but broke down for complex geometries. Ufimtsev's method worked for any shape, no matter how angular or irregular, as long as you could describe its surfaces mathematically. The genius of his approach was treating an aircraft not as one large radar target, but as a collection of smaller reflecting elements, panels, edges, gaps, each scattering radar waves according to precise geometric rules. Add up all those individual reflections using Ufimtsev's equations, and you could predict the total radar signature of any aircraft from any angle. More importantly, you could design aircraft specifically to minimize that signature. Soviet engineers looked at Ufimtsev's work and saw theoretical mathematics with no immediate military application. Their air defense doctrine relied on powerful ground-based radars that could burn through jamming and detect aircraft at long range. Why worry about reducing aircraft radar signatures when you could just build stronger radars? The Americans, the Soviets assumed, were pursuing the same logic: bigger radars, faster missiles, more powerful jamming. Nobody was trying to make aircraft disappear. The CIA obtained Ufimtsev's paper in 1971 through routine intelligence gathering. Soviet scientific journals circulated internationally, and the Moscow Institute of Radio Engineering published openly to maintain academic credibility. A translator at the Air Force Foreign Technology Division converted Ufimtsev's Russian into English, noting it as potentially relevant to radar cross-section studies, without grasping its full significance. The translation, all 233 pages, entered the Defense Technical Information System with classification level, unclassified. For 4 years, it sat in archives while American engineers pursued conventional stealth approaches: radar-absorbent coatings, curved surfaces, careful engine inlet design. These methods reduced radar signatures incrementally. A few decibels here, a percentage point there. Nothing revolutionary. Nothing that changed the fundamental rules of air combat. When Dick Cantrell finally pulled that translation off the shelf in 1975, Ufimtsev was still teaching in Moscow, completely unaware his equations were about to transform American military aviation. The Soviet physicist had moved on to other theoretical problems: antenna design, wave propagation in complex environments. His 1962 diffraction paper was ancient history, cited occasionally in academic journals, but never by military researchers. The irony was profound. Soviet radars in 1975 were the best in the world. The SA-6 gainful system could track multiple targets simultaneously while resisting electronic countermeasures. Soviet missile designers had created weapons that could kill aircraft at 60,000 feet or skim the terrain at 100 feet altitude. Their air defense network stretched from East Germany to Vladivostok. Thousands of radar installations linked into an integrated early warning system. But they'd given away the mathematical key to defeating all of it. Ufimtsev's equations, published openly and dismissed as theoretical curiosity, had handed America a blueprint for aircraft that could fly through Soviet radar coverage without triggering a single alarm. The Russians had solved the stealth problem 13 years before the Americans even knew they needed it solved. They just didn't recognize what they'd discovered. Denys Overholser stared at the computer printout in April 1975 and knew he'd found something the aviation world had never seen. The numbers from his radar cross-section calculation program, nicknamed Echo 1, showed an aircraft design with a signature 1,000 times smaller than any operational fighter. The shape responsible for those numbers looked like someone had carved a jet from flat sheets of metal and assembled it at random angles. It had all the aerodynamic grace of a doorstop. Overholser's breakthrough was realizing that Ufimtsev's equations demanded faceted surfaces, not the smooth curves aircraft designers had preferred for 40 years. Traditional jets featured rounded fuselages and swept wings because engineers assumed smooth shapes reduced drag and improved flight characteristics. But smooth curves were radar nightmares. They scattered electromagnetic waves in every direction, ensuring some energy always bounced back to enemy receivers. Ufimtsev's math proved that flat panels meeting at precise angles could channel radar energy away from the source entirely, like billiard balls banking off carefully angled cushions. The design Overholser created looked two-dimensional from certain angles, as if someone had drawn a fighter jet and forgotten to add depth. The fuselage consisted of 4 flat sides meeting at sharp Chinese, the edges where panels intersected at steep angles. The wings were flat triangular surfaces, canted inward at 40 degrees. No curves anywhere, no smooth transitions. Every surface was a flat panel. Every intersection, a hard edge positioned to deflect radar waves sideways, upward. Anywhere except back toward Soviet radar dishes. He called it a faceted design, borrowing terminology from gem cutting. Just as a diamond's facets reflected light in controlled directions, Overholser's panels would reflect radar energy away from threats. The aircraft would have only 4 primary radar lobes, 4 narrow angles where reflected energy concentrated, instead of the omnidirectional, scattering conventional aircraft produced. Point a radar at this aircraft from 45 degrees off its nose, and the reflected energy would scatter at 90 degrees, missing the radar receiver entirely. Ben Rich brought Overholser's design to a meeting with Air Force officials at the Pentagon in June 1975. The generals looked at the angular sketches and winced. One asked if it could actually fly. Rich admitted he didn't know. They'd need wind tunnel tests to find out, but the radar cross-section predictions were undeniable. 0.01 square meters frontal aspect, smaller than a hummingbird. Soviet early warning radars scanning for targets with signatures of 10 to 25 square meters would see nothing but background noise. The Air Force issued a contract in November 1975 for experimental development under the code name Have Blue. Lockheed would build 2 subscale prototypes to prove the faceted concept worked. Overholser's team had 6 months to turn angular sketches into actual aircraft. They started with wooden models, coating them with radar reflective material and testing them on radar ranges at Lockheed's Rye Canyon facility. The models confirmed Echo 1's predictions. The faceted shape was nearly invisible to radar at most angles. Building a flyable version was harder. The facets created conflicting structural requirements. Sharp Chinese wanted to crack under stress. Flat panels needed internal bracing that added weight. The inward canted wings generated almost no lift at low speeds. Overholser worked with aerodynamicist Dick Scherer to add small stabilizers and adjust panel angles for minimal lift characteristics. They calculated the aircraft would need a takeoff speed of 180 knots and would handle like a brick with the glide ratio of a streamlined anvil. None of that mattered if the radar signature worked. Overholser had transformed Ufimtsev's abstract mathematics into physical reality, a shape that could hide aircraft from the most sophisticated detection systems on Earth. Whether that shape could actually fly was a problem for test pilots to solve. Bill Park climbed into Have Blue's cockpit on November 16, 1977, knowing the aircraft beneath him shouldn't be able to fly. The prototype sat on the tarmac at Groom Lake, Nevada, the remote Air Force facility known as Area 51, looking like an experimental sculpture rather than a combat jet. Its flat-faceted surfaces caught the desert dawn light at odd angles, creating sharp shadows that made depth perception difficult. Park had flown experimental aircraft for 17 years, including the SR-71 Blackbird. Nothing had looked this aerodynamically suspect. The first Have Blue prototype weighed 12,000 pounds and measured 38 feet long with a 22.5-foot wingspan. Its 2 General Electric J85 engines, the same power plants used in the T-38 trainer, generated 5,900 pounds of thrust combined, barely enough to overcome the faceted shape's terrible lift-to-drag ratio. Wind tunnel tests at Lockheed had revealed a fundamental problem. The angled surfaces that made the aircraft invisible to radar also made it unstable in all three flight axes. The aircraft wanted to pitch, roll, and yaw simultaneously the moment it left the ground. Lockheed's solution was fly-by-wire, a computer system that interpreted Park's control inputs and made hundreds of tiny adjustments per second to keep the aircraft stable. Without that computer, Have-Blue would tumble out of control within seconds. Park had no backup controls, no mechanical cables connecting his stick to control surfaces. If the computer failed, he'd have to eject immediately. He advanced the throttles and accelerated down Groom Lake's runway. At 180 knots, Park pulled back on the stick. Have-Blue lifted off grudgingly, climbing at a shallow angle. The fly-by-wire system worked. The aircraft responded to his inputs without the violent instability predicted by raw aerodynamic calculations. Park leveled at 10,000 feet and radioed the test range crew. 30 miles away, air defense radars trained their beams on his position. The radar operators saw nothing. Their screens showed empty sky where Have-Blue should have appeared as a bright blip. Park flew a racetrack pattern for 15 minutes, while ground stations confirmed the result from multiple angles. The faceted aircraft had a radar cross-section below 0.01 square meters, exactly as Overholser's calculations predicted. Soviet radar systems, searching for targets with signatures measured in tens of square meters, couldn't detect Have-Blue even when operators knew exactly where to look. Park completed 9 successful test flights over 3 months, validating stealth technology's core principle. But on May 4, 1978, during the 10th flight, Have-Blue's fly-by-wire system suffered a software glitch on final approach. The aircraft pitched up sharply, stalled at 200 feet, and dropped onto the runway gear up. Park ejected a split second before impact, parachuting safely as the prototype slid 2,000 feet in a shower of sparks. The airframe was destroyed, but engineers recovered enough data to confirm every facet worked as designed. The second Have-Blue prototype flew on July 20, 1978, with test pilot Ken Dyson at the controls. Over the next 6 months, Dyson and Park completed 52 additional test flights, pushing the stealth aircraft to 15,000 feet altitude and 365 knots airspeed. They validated radar cross-section performance from every angle, confirmed the aircraft could operate at night, and tested its infrared signature against heat-seeking sensors. On July 11, 1979, during a landing approach, the second prototype's landing gear malfunctioned. Dyson ejected safely, and the aircraft crashed into the Nevada desert, marking the end of Have-Blue's test program. Both prototypes were destroyed, but they'd proven the impossible. Faceted geometry could make aircraft invisible to radar. The Air Force immediately authorized full-scale development of an operational stealth fighter. Lockheed had 18 months to turn Overholser's radical concept into a weapon. General William J. Perry stood before the Defense Systems Acquisition Review Council in November 1978, requesting $1.2 billion for an aircraft that looked unflyable and relied on technology the Air Force had never used operationally. Perry, serving as Undersecretary of Defense for Research and Engineering, was staking his reputation on faceted stealth. 2 Have-Blue prototypes had demonstrated radar invisibility, but both had crashed. Now, Perry wanted production funding for 59 operational aircraft before anyone knew if the design could survive combat conditions. The request faced immediate skepticism. Pentagon officials saw the Have-Blue photographs, the angular surfaces, the absence of curves, the tiny wings canted at unnatural angles. Veteran fighter pilots called it the wobbly goblin and questioned whether the faceted shape could maneuver in combat. The F-15 Eagle, entering service in 1975, could pull 9G turns and accelerate to Mach 2.5. Perry's stealth aircraft, according to preliminary specifications, would max out at Mach 0.92 and handle like a cargo plane. Why spend billions on a slow, unmaneuverable jet that couldn't dogfight? Perry's answer focused on survivability rather than performance. Soviet integrated air defense networks in 1978 stretched across Eastern Europe and Soviet territory in overlapping layers. SA-2, SA-3, SA-ISK, and SA-8 missile batteries covered high, medium, and low altitudes. MiG-23 and MiG-25 interceptors patrolled with look-down radars that could spot low-flying attackers. American strike aircraft, F-117s, A-6 intruders, had to penetrate those defenses using terrain masking, electronic jamming, and anti-radiation missiles. Losses would be catastrophic in any sustained air campaign. A stealth fighter changed the calculus entirely. An aircraft with a 0.01 square meter radar cross-section could fly straight through Soviet air defense zones without triggering acquisition radars. It wouldn't need to jam enemy systems, wouldn't need to fly nap of the earth through mountain valleys, wouldn't need fighter escorts. It could cruise at 20,000 feet, invisible to radar, and strike command centers, communications nodes, and surface-to-air missile sites before defenders knew an attack was underway. First night of war missions that would cost dozens of conventional aircraft could be accomplished by a handful of stealth fighters with zero losses. The strategic implications sold the program. Perry secured initial funding in December 1978 under the codename Senior Trend. Lockheed received a contract to develop the F-117A Nighthawk, the operational version of Have Blue, with first deliveries scheduled for 1982. The program remained classified at the highest levels. Congress received only vague budget descriptions. Even most Air Force personnel didn't know stealth aircraft were under development. Ben Rich led the Lockheed team expanding Overholser's prototype design into a combat-ready aircraft. The F-117A would be larger than Have Blue, 65.9 feet long with a 43.3-foot wingspan, and carry 5,000 pounds of precision-guided weapons in an internal bay. Two General Electric F-404 engines, the same power plants used in the F-A-18 Hornet, would provide 21,600 pounds of thrust. The faceted geometry would remain identical to Have Blue's proven design, flat panels meeting at precise angles, sharp Chinese running along the fuselage, wings canted inward at 40 degrees. The biggest challenge wasn't aerodynamics or radar signature. It was maintaining absolute secrecy while building 59 aircraft. Rich needed manufacturing facilities, test ranges, and pilot training programs completely hidden from Soviet intelligence. The solution was Groom Lake, the remote Nevada facility where Have Blue had flown. The Air Force expanded Area 51's infrastructure, building new hangars with special security protocols and extending the runway to accommodate operational aircraft. Perry's gamble was underway. If the F-117 worked, America would possess a strategic advantage unprecedented in military aviation. If it failed, $1.2 billion would vanish into the desert, along with Perry's career. The first F-117A fuselage took shape inside Building 602 at Lockheed's Burbank facility in January 1980, assembled by workers who had no idea that what they were building. Lockheed divided the aircraft into sections: forward fuselage, center fuselage, aft fuselage, wings, and manufactured each piece in separate facilities with different security clearances. Machinists fabricated aluminum panels to precise specifications without seeing engineering drawings showing the complete aircraft. Only workers at Groom Lake, where final assembly occurred, understood they were building something revolutionary. The faceted design created manufacturing nightmares. Conventional aircraft featured compound curves that distributed structural loads naturally. The F-117's flat panels, meeting at sharp angles, concentrated stress at the Chinese, the edges where surfaces intersected. Engineers reinforced those junctions with titanium stringers and aluminum spars, adding weight that reduced payload capacity. Each panel had to align perfectly. Gaps larger than 0.030 inches would create radar reflections that compromise stealth. Workers used laser alignment tools to position panels within tolerances measured in thousandths of an inch. The radar absorbent material coating presented even harder challenges. Lockheed developed a substance resembling black rubber that absorbed radar energy instead of reflecting it. The material, officially designated as have glass, consisted of microscopic iron spheres suspended in a polymer matrix. Radar waves penetrating the coating induced electrical currents in the iron particles, converting electromagnetic energy into heat that dissipated harmlessly. Workers applied have glass by hand in multiple thin layers, waiting 24 hours between coats for proper curing. The process took 3 weeks per aircraft. Those coatings were fragile. Rain eroded them. Temperature changes caused cracking. Even careful handling during maintenance could damage the radar absorbent surface. The F-117 would require constant inspection and touch-up, making it one of the highest maintenance aircraft in Air Force inventory. But without those coatings, the faceted aluminum underneath would reflect radar like a mirror, destroying the stealth advantage entirely. Final assembly occurred inside a new hangar at Groom Lake, constructed specifically for the F-117 program. The facility featured climate-controlled bays where temperatures remained constant at 68 degrees Fahrenheit, essential for radar-absorbent material application. Armed guards controlled access through biometric scanners. Workers signed non-disclosure agreements threatening prosecution for unauthorized information release. Nobody was permitted to take notes, photographs, or discuss their work outside secure facilities. The internal weapons bay required ingenious engineering. External weapons pylons created massive radar reflections, so the F-117 carried everything internally. Laser-guided bombs, GPS-guided munitions, even the targeting system. Lockheed designed trapeze-shaped bomb racks that rotated weapons down into the airstream, released to them, and retracted back inside within 1.2 seconds. During that brief exposure, the open bay doors increased radar cross-section to roughly 1.0 square meters, still 25 times smaller than a conventional fighter. The moment doors closed, the aircraft vanished from radar again. Each F-117 cost $42.6 million in 1983 dollars. Expensive, but not extraordinarily so, compared to the F-15's $29.9 million price tag. The real expense was infrastructure. Secure hangars at Tonopah Test Range, where the operational squadron would deploy, specialized maintenance equipment, pilot training simulators, and the security apparatus that kept 59 stealth fighters hidden from Soviet satellites and intelligence services. The first operational F-117A, tail number 79-10780, was delivered to the Air Force on August 23, 1982. Test pilot Hal Farley flew it from Groom Lake to Tonopah, a 175-mile journey across the Nevada desert. By 1983, Lockheed was delivering one F-117 per month. The 4450th Tactical Group, the unit assigned to operate the stealth fighters, began training pilots in absolute secrecy. Crews flew only at night, avoided populated areas, and returned to Tonopah before dawn. For 6 years, 59 operational stealth fighters flew combat training missions while the world had no idea they existed. Major Al Whitley rolled the F-117A into a 30-degree bank over the Nevada desert in March 1983 and felt the aircraft try to kill him. The fly-by-wire computer corrected immediately, applying opposite aileron and rudder to stop the uncommanded roll. But the message was clear. Without that computer, the Nighthawk was aerodynamically lethal. Whitley was one of 12 pilots selected for the 4450th Tactical Group, the stealth fighter squadron that didn't officially exist. He'd flown F-111s and A-7 Corsairs, both stable aircraft that forgave pilot errors. The F-117 forgave nothing. The problem was fundamental physics. Those flat-faceted panels that made the aircraft invisible to radar generated almost no lift. The inward-canted wings produced vortices that disrupted smooth airflow. The angular fuselage created turbulence that destabilized flight in all 3 axes simultaneously. In straight and level flight at 20,000 feet, the F-117 wanted to pitch nose down while rolling left and yawing right, all at once. Conventional control surfaces couldn't correct fast enough. Human reflexes were too slow. Lockheed's solution was a quadruple redundant fly-by-wire system running through 4 independent computers. Each computer received inputs from Whitley's control stick and calculated the precise control surface movements needed to execute his commands while keeping the aircraft stable. The computers compared their calculations, and if all 4 agreed, control surfaces moved accordingly. If one computer disagreed, the other 3 outvoted it. If 2 computers failed, the system automatically reduced to degraded mode with limited maneuvering capability. If 3 computers failed, Whitley had about 2 seconds to eject before the aircraft departed controlled flight. Test pilots discovered other quirks during the operational evaluation phase. The F-117 had no radar. Radar emissions would reveal the aircraft's position, so pilots navigated using an infrared targeting system that displayed terrain as grainy black and white video. Flying at night through mountainous terrain with no visual references except infrared imagery required intense concentration. Several pilots reported spatial disorientation during their first night flights, unable to distinguish ground from sky on the infrared display. The aircraft's low-speed handling was treacherous. Approach speed was 172 knots with no margin for error, too slow, and the aircraft stalled with insufficient altitude for recovery. Too fast, and the landing gear, built lightweight to minimize radar signature, risked collapse on touchdown. The narrow wings generated almost no lift at landing speeds, so the F-117 descended at 1,500 feet per minute on final approach, nearly triple the descent rate of conventional fighters. Pilots described it as flying a controlled crash. Combat maneuverability was essentially non-existent. The F-117 had a maximum load factor of 6 Gs compared to the F-15's 9 Gs. Maximum speed was 617 miles per hour at altitude. Fast for a subsonic aircraft, but useless against supersonic interceptors. If a MiG somehow detected a Nighthawk and engaged, the stealth fighter couldn't dogfight and couldn't run. Its only defense was remaining invisible. That invisibility came with a price measured in maintenance hours. After each flight, crew chiefs inspected every inch of radar-absorbent coating for damage. Rain missions required complete aircraft wipe-downs, followed by coating repairs that took 12 hours. The half-glass material degraded naturally over time, requiring periodic reapplication that grounded aircraft for days. Each F-117 needed 120 maintenance hours per flight hour, 4 times the F-15's requirement. But when everything worked, the aircraft was magic. Whitley flew training missions straight through simulated Soviet air defense zones, while ground controllers watched F-117s pass within 5 miles of radar installations without triggering alarms. The faceted surfaces and radar-absorbent coatings performed exactly as Overholser had calculated. The Nighthawk was invisible. It just flew like a brick wrapped in tinfoil, held aloft by computers and pilot skill in roughly equal measure. Major Greg Feast flew F-117A tail number 850816 into Panamanian airspace on December 20, 1989, carrying the first bombs ever dropped in anger by a stealth aircraft. Operation Just Cause, the invasion to depose Manuel Noriega, was supposed to demonstrate stealth technology's combat effectiveness. Instead, it revealed how unprepared the Air Force was to employ a weapon this radical. FEST's mission was to drop a single 2,000-pound GBU-27 Paveway 3 laser-guided bomb on the Rio Hato barracks, stunning Panamanian Defense Forces soldiers before Army Rangers parachuted onto the adjacent airfield. The mission profile seemed straightforward. FEST would fly from Tonopah Test Range to Panama, refuel twice from KC-135 tankers over the Gulf of Mexico, approach Rio Hato at 20,000 feet, designate the target with his infrared laser, and release one bomb. The GBU-27's laser seeker would guide it onto the barracks courtyard. The explosion would disorient defenders for exactly 120 seconds, long enough for Rangers to secure the airfield. Simple precision strike, the mission F-117s were designed to execute, But when Fest arrived over Rio Hato at 1 a.m. local time, his infrared targeting system showed clouds obscuring the target area. He couldn't see the barracks, couldn't designate the impact point, couldn't execute the mission as planned. Feast made 3 passes, waiting for a break in the clouds. On the 4th pass, he glimpsed the target briefly and designated it, releasing his bomb 2 seconds later. The GBU-27 fell away, tracking toward the laser spot Feast held on target. The bomb impacted 300 feet from the intended aim point, exploding in soft earth instead of the barracks courtyard. The blast was loud but caused minimal casualties. Panamanian soldiers, already alert due to noise from approaching C-130 transports, were startled but not incapacitated. The Rangers jumped into immediate ground fire. The mission wasn't a complete failure. Rio Hato fell within hours, but it wasn't the surgical demonstration of stealth precision the Pentagon had envisioned. A second F-117, flown by Captain John Leahy, struck a different target at Rio Hato simultaneously. His bomb missed by 400 feet, hitting empty jungle. 2 stealth fighters, 2 bombs, 0 direct hits on high-value targets. The Air Force classified the mission results immediately and released only vague statements about stealth aircraft participating in Just Cause. News reports mentioned radar-evading fighters without specifics. The F-117's existence became public knowledge, but its actual performance remained classified. Soviet military intelligence analyzed every scrap of information from Panama. They knew American stealth aircraft had participated. Journalists in Panama City had heard the explosions and seen nothing on radar. GRU analysts examined bomb crater patterns, interviewed Panamanian military personnel, and reviewed radar logs. Their conclusion? The Americans possessed operational stealth technology that defeated radar detection. But how did it work? The Soviets had no answer. Soviet engineers had ignored Ufimtsev's equations for 27 years. Now they scrambled to understand what their own physicist had discovered decades earlier. Russian radar designers dug out Ufimtsev's 1962 paper and began calculating retroactively. They realized the Americans must be using faceted geometry, the only approach that matched observed radar characteristics. But Soviet aerospace doctrine had spent 40 years optimizing aircraft for speed and maneuverability. Redesigning combat aircraft around stealth principles would require abandoning decades of engineering philosophy and rebuilding entire production lines. The Panama strikes, despite their tactical flaws, achieved a strategic objective the Air Force hadn't anticipated. They paralyzed Soviet air defense planning. Every SA-6 battery, every MiG-29 interceptor, every integrated air defense network the Soviets had built suddenly faced an enemy they couldn't see. The Americans had aircraft that could appear anywhere without warning. Panama was just the beginning. Captain Marcel Kurdavid sat in his F-117A cockpit on the taxiway at King Khalid Air Base, Saudi Arabia, at 2:51 a.m. on January 17, 1991, watching 35 other Nighthawks taxi into position ahead of him. Desert Storm's air campaign was scheduled to begin in 39 minutes, with the largest coordinated strike in Air Force history, 750 aircraft hitting targets across Iraq and Kuwait simultaneously. But only the F-117s would strike Baghdad itself. The Iraqi capital bristled with more concentrated air defenses than any city on Earth. 3,000 anti-aircraft guns, 60 surface-to-air missile batteries, overlapping radar coverage from ground level to 80,000 feet. Conventional aircraft couldn't survive there. The faceted stealth fighters would find out if Overholser's geometry actually worked against a fully alerted enemy. The 37th Tactical Fighter Wing, the F-117's operational designation in Saudi Arabia, had received targets deep inside Baghdad's defended perimeter. The Air Defense Operations Center, the National Telephone Exchange, military command bunkers, and the Ba'ath Party headquarters. Each target sat within 5 miles of dozens of SAM sites. Iraqi radar operators would be watching their screens, expecting American strikes. But they'd be watching for the massive radar signatures of F-15s, F-16s, and F-111s, aircraft with radar cross-sections between 5 and 25 square meters. They wouldn't see the Nighthawks at 0.01 square meters. Kurdavid lifted off at 3:10 a.m. and turned northwest toward the Iraqi border, climbing to 23,000 feet. His targeting system showed terrain features in grainy infrared, desert roads, isolated buildings, the occasional vehicle. At 3:30 a.m., he crossed into Iraqi airspace. His radar warning receiver, the system that detected enemy radar beams, remained silent. Iraqi early warning radars were sweeping the sky, searching for American aircraft they knew were coming. Their beams washed over Kurdavid's F-117 and found nothing. The faceted surfaces scattered radar energy sideways. The radar absorbent coating absorbed what little energy struck perpendicular to the panels. On Iraqi radar screens, the sky showed empty. At 3:43 a.m., Kurdavid reached Baghdad and began his attack run on the telephone exchange. The city glowed in his infrared display. Street lights, vehicle headlights, heat signatures from buildings. Anti-aircraft fire erupted randomly across the city as Iraqi gunners fired blindly at sounds of distant explosions from Navy Tomahawk cruise missiles hitting targets on Baghdad's outskirts. Kurdavid ignored the tracers arcing into empty sky and focused on his targeting crosshairs. He designated the telephone exchange's center, waited for the laser seeker to lock, and released a single GBU-27 bomb. The 2,000-pound weapon fell for 38 seconds, tracking the laser spot Kurdavid held on target. At 3:44 a.m., it punched through the exchange's roof and detonated inside, severing communications between Iraqi Air Defense Headquarters and SAM batteries nationwide. 6 other F-117s struck similar targets within 2 minutes. Command centers, communications nodes, radar installations, decapitating Iraq's integrated air defense network before controllers understood they were under attack. Over the next 43 days, F-117s flew 1,271 sorties into Iraq, striking 1,664 targets with 0 aircraft losses. They hit bridges in downtown Baghdad, while anti-aircraft fire lit up the sky around them, always missing because gunners were shooting at radar ghosts. They destroyed hardened aircraft shelters at Iraqi air bases, knocking out MiG-29s before they could scramble. They demolished Scud missile storage facilities, chemical weapons plants, and Saddam Hussein's presidential palaces. Iraqi integrated air defense, the system Soviet engineers had spent decades perfecting, never successfully engaged a single F-117. Coalition aircraft losses totaled 75 during Desert Storm, but none were stealth fighters. The faceted geometry Denys Overholser had sketched in 1975, the equations Pyotr Ufimtsev published in 1962, the radar absorbent coatings Lockheed's engineers applied by hand in climate-controlled hangars. All of it worked exactly as designed. The F-117 hadn't just validated stealth technology, it had rendered conventional air defense obsolete. Soviet radar operators watched CNN footage of Baghdad burning and understood their entire defensive strategy had been defeated by aircraft they couldn't see. Ufimtsev's dismissed mathematical curiosity had changed warfare forever. The invisible fighters had proven unstoppable.